This is our project pipeline to complete this project. What OS has done is in yellow, what I have done is in blue, and what we have both collaboratively worked on is in green.
Hello, my name is OS, and what I worked on is the data collection and the data preparation.
My name is Naba, and I carried out the fine-tuning scripts and the optimization scripts. We both worked on the evaluation and demo of our final GUI.
This file creates an organized workspace for combining two dysarthric speech datasets. The first dataset is TORGO, which contains English dysarthric audio and transcriptions from the University of Toronto. The second dataset is EasyCall, which contains Italian recordings of basic smartphone commands, such as open contacts, start call, end call, obtained from Italian Institute of Technology, the University of Ferrara, and the San Anna Hospital of Ferrara. This section creates raw data directories, as well as output directories, audio, and transcription files. This section is a loop that creates the directories. This section stores the metadata, which is the data that describes other data. This section also resamples audio to 16 kHz, which is a sampling rate Whisper works with. Lastly, the configuration file is saved. Moving on to step 2, a script that organizes the TORGO database. We create a function called extract if needed, which checks for a compressed dataset and extracts if required. It does this by searching for zip and tar files. The next important section of the script searches recursively for all WAV files and checks if any audio files are found. Next, we automatically categorize speakers into two research groups: dysarthric speakers, individuals with speech motor disorders, and control speakers, which are not impaired. Finally, it tracks total files processed and also counts dysarthric versus control speakers. We repeated the same process to organize the EasyCall database. The overall objective of the script 4 is to merge and process two speech datasets, TORGO in English and EasyCall in Italian. One particularly important function in the script is validate and process, which takes an audio file and its transcript, checks if both are present and valid, and shows the audio of reasonable length between 0.5 and 30 seconds, and that it contains audible speech by checking its loudness through the root mean squared, the RMS value. This function also standardizes each audio sample, so every file is at a sample rate of 16,000 Hz and normalized in volume, making them ready for further machine learning processing. If the RMS value is below a threshold of 1/1000, it's assumed the recording is either silent, corrupted, or otherwise unusable, and the sample is skipped. This check helps filter out problematic data, ensuring the training set has minimally viable speech content.
Thank you, OS, for explaining your section of the code. This is the fifth and core script, which carries out fine-tuning on the combined datasets. The script starts by gathering the training material. It loads the dysarthric speech datasets in the load splits function. This next section of the script prepares the base or pre-trained Whisper model. It converts all of the audio and text into numbers that the computer can understand in the prepare dataset function. Here, we set up gentle learning rules with a slow learning rate and a small batch size to make careful adjustments. The most critical arguments or settings are highlighted in yellow on the right. The tiny learning rate of 5 parts per million makes adjustments so we don't break Whisper's existing knowledge while adapting it to impaired speech. A gradient accumulation of 4 steps effectively gives us a larger batch size despite memory limits, making training more stable. Gradient checkpointing saves memory by recomputing some of the values instead of storing them, allowing us to train larger models. These three work together to enable safe, stable fine-tuning on limited hardware while specializing the model for dysarthric speech recognition. The actual learning happens when trainer.train runs. The model repeatedly listens to dysarthric speech samples, tries to transcribe them, and then compares its guesses to the correct transcripts. Each time it makes a mistake, it slightly adjusts its internal settings to better recognize impaired speech patterns. This process continues and continues for multiple passes through the data, which we set to 10, gradually specializing the model for assisted speech recognition while preserving its original knowledge. Finally, this is step 6 of the pipeline. It converts the fine-tuned Whisper model into a faster, smaller format that is used for deployment. After step 5 of training, we have a fine-tuned Whisper model that understands dysarthric speech. However, it's in the PyTorch format, which is slow and also very large. The inference is quite slow on the CPU, which will increase latency by about 5 to 10 seconds. However, we introduced step 6 to keep the same model quality, but use a C translate 2 format, which is optimized for inference. An INT8 quantization makes the model 4 times smaller and also introduces a 3 times faster inference using faster Whisper. This is the core conversion using C translate 2 with INT8 quantization. Quantization reduces the model from 32 bits to 8 bits, making it 4 times smaller and 3 times faster while maintaining nearly the same accuracy. This allows our model to run efficiently on consumer hardware and also provide real-time speech recognition. The script creates a complete package ready for deployment.
The loss function is a mathematical function that measures the difference between a model's predicted value and the actual true value. At the beginning of training, the loss function circled in red is 9.8, which is extremely high. However, as training progresses, the loss function reduces to a value of 0.6, showing an improvement of accuracy by 94%.
Help, we are testing a demonstration for our project.
Help, we are testing a demonstration for our project.
Help, we are testing a demonstration for our project.
We are testing a demonstration for our project.
Testing. I need help. We are testing a demonstration for our final project.
We are testing a demonstration for our final project.
Computers make art, and I would like to find out how they do that. Three-dimensional art, and
I would like to find out how to do that.
Computers make art. And I would like to find out how they do that. Three-dimensional art.
Computers make art and I would like to find out as they do today.
Feel like a shopper. I will succeed. Coco, we can. I'm gonna get long. Feel like a shopper. I will succeed. Coco, we can.